All right, so we're going to double down on induction and recursion today and just try to get this down pat. I know many of you have seen this before, but sometimes not everyone has, or people have seen it in different ways. In any case, um, if you find this too simple, then just enjoy it while it lasts. Okay, but I really think that getting the basics down is the best thing, and then hopefully the later developments will then kind of feel more natural. So, okay, so last two times, I suppose, uh, we discussed sort of sorting and searching and sorting. But along the way, we talked about some more generic things like big O notation, recursion trees, um, and the sort. Uh, and a big thing, or at least something that we sort of worked up to, was doing our first recursive algorithm. An algorithm, of course, you've all seen or likely have seen before and likely have used before. Um, but one important step that we'll really focus on today is this recursive specification and this recursive aspect of it. And of course, this algorithm you've seen before, so maybe I'll try to put you in new situations today to try to challenge this thinking process style a little more. So, okay, let me just give a really brief introduction to induction then. So, all right, let's say that you're climbing a bunch of stairs. Okay, so you have some staircase like this. That's not a great staircase. Just leave the picture on the right. Okay, uh, so how would you explain to someone how to climb a long staircase? Not a trick question, just yeah. Okay, so how would you describe one step? It might be like, yeah, go ahead. Yeah, all right, okay, that's fine. So I think this is what we had in mind. I took the time to write out, I don't know, trying to explain someone taking a step, right? But the real key idea that I'm sure everybody realizes is that you would explain how to take one step, and you wouldn't then explain how to take the second step as if it were different. You just say, oh, do the same thing again and again and again, and I promise you'll get to the top, right? That's how everyone would do this. So the key point is that you recognize that every step is identical. There's no point in making distinctions, right? And and I guess really the bold claim, if that's a fair terminology, is the claim that this will work in perpetuity and will eventually get you to the top. Okay, and the question is, okay, how do we actually prove this? Okay, so all right, here would be a sort of proof by induction. Of course, it's not very formal because climbing stairs is not very formal. This is just obviously a warm up to get us thinking, right? But when you're proving something by induction, and I'm just going to assume that the steps work for one step and focus on this inductive step. Well, you guys have all heard this before. You start with some kind of base case, right? Like a minimal case. It'll be motivated more in a second. But for us, that could be one stair, or I could have written it so that it's just zero stairs. And just say, okay, for one stair, yada, 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 these steps would work. Okay. The more interesting case is, okay, how do you prove that these instructions, again, proof with quotations around it, it's not a real claim. How do you prove that this paragraph of instructions will scale to any arbitrary number of stairs, right? I mean, it's obvious, but how do you actually articulate it? So, you're looking at this general case of n greater than one stair. One stair was so simple, you can just handle it directly. And I guess the challenge is you want to make an argument where, like, okay, you can imagine if you had to do two stairs, it would only be a little bit longer than our one stair. Three stairs, maybe a little bit longer than that. But if it's 100 stairs, you want some kind of argument, sort of the length of which is independent of n, right? You don't want to sit around all day arguing, it's going to work for the 75th stair, the 76th, let alone n is 1,000, n is 100,000. So, okay, how do we address this general case, well, you might do something like this. We kind of assume as given that the instructions work for one step. No point in debating that for pedagogical reasons. Okay. And the key point is that after you take one step, n minus one steps are left. Okay, say, okay, I feel very good, and I'm willing to labor and argue in detail about this one step, at which point there's n minus one steps left, right? And the magic bullet is here you say, okay, by induction on n, I'm going to assume the instructions work for any staircase of n minus one remaining steps. All right, this is what induction lets you do. So as you kind of build up these proofs incrementally, you can assume that the smaller cases are always correct. The reason why we have to handle the base case explicitly, because there was no smaller case beneath that. So there has to be kind of a bottom. Okay? And the principle of induction says, this is fine, this is valid. If you want to be a deep philosopher, you can question induction, but we won't question induction here. And then we're done. Okay, so maybe not a great example because it's a little bit informal, right? But the point is, when we do a proof by induction, you can assume it works for all the smaller cases. Okay, you just have to worry about taking one more step. Okay, it's really more of an analogy than a proof. Maybe this, especially if you haven't seen it before, will be a more interesting exercise. Okay, so how many of you have heard of the Towers of Hanoi problem? Okay, so this is a famous puzzle, and I think it's attributed to a French person like 150 years ago or something. But so the legend is that there's like three posts in Hanoi that are very tall, and these like golden brass rings that are on top, and it takes a whole day to move one ring at a time. And your goal is to move all the rings from the first post to the second, but there's a rule. The rule is that the rings always have to be in order. So like in the sense that you can't put a bigger ring on a smaller ring. So you can do something like this where you move the smallest ring to B, right? But then you look at this next ring, you're not allowed to put it there. You'd only be able to put it there. Okay? And then if you want, you could put B on top like that, but you can only have each post has to have rings sort of in order. You can only have a smaller ring on top of a bigger ring. You can only move one ring at a time. Okay, and the puzzle is like, okay, if these monks or something can only move one ring a day, how long would it take or something? Yeah. All right, so this is a fun puzzle, and I want to give you all a chance to think about it for a moment. One ring at a time. So it's like we're trying to make an algorithm, more so than answer a puzzle. And your computer can like look at the posts and see what's on top and things like this. But it can move only one ring at a time. Really, the point is, first, is it even possible to move everything over? Right? And second, we'll address that next. Can we really do it with a minimum number of rings? So there's few enough rings that you might be able to eyeball it. Okay. Does anyone have some ideas or suggestions? Or we can even just address this particular example, right? What should be the first step? What ring should I move first? Well, you have to move the top one, but should I move it to B or C? Either, okay, I'll move it to B. Okay? And then I guess you probably want to move the second to top one, and I guess that has to go to C. Okay, now what? Okay, B to C. Okay. A to B. C to A. C to B. A to C. Okay. This is getting laborious. Hopefully we'll eventually make it through. I guess now A to C is what? Okay. You can imagine trying to do this thing, and maybe it'll work. Okay. You can keep moving, so on, and so forth. Uh, but it feels like it's going to take a little while, and one thing I've already learned this week is that these 15-minute classes are very short. So we're going to try to take a shortcut. Okay. Here is a different kind of algorithm. I mean, it might implicitly be the same algorithm. Okay. That maybe you'll get very used to soon. I have n rings on ring A. Okay. I'm going to move the top n minus 1 rings to post C, and I'll move the bottom one over, and I'll move the top n minus 1 back. Obviously, I cheated, right? But I'm going to assume by induction I can move to n minus 1, and that will at least let me justify that it's possible. So let's do this a little more slowly. If I want to make a recursive algorithm, as always, I force you to write out some kind of recursive spec. Okay? So that when I say I move n minus 1 rings from something to the other, I'm very precise about it, and I know exactly what I'm guaranteed. Okay? So I left this blank for all of you to fill in, but it's never too exciting. I just give it some kind of descriptive name, so I'm writing T of H to stand for Towers of Hanoi. Okay? And then usually the next step is to try to identify the input parameters. Okay, okay, so maybe n, number of poles, 3. Okay, let's try that. And then now I need to write a sentence describing what I really mean by this. Okay, I can start. Usually it's not too interesting. We're more or less stating the problem. Given n rings, I guess n 3 poles, right? Because those are 2 parameters. What do you want the output to look like? All right, move all the rings from pole B. Move all. All right, so I think this is right, but it also brings up a point, which is at some level, B is not clearly defined because we just wrote 3. So maybe, because somewhere along the lines, we might actually want to, at some level, sort of like relabel the pole so I can move from a different pole to another. So I think we'll find it more convenient to write A, B, C, and write something a little more precise, like given n rings on pole A, move all the rings to pole B, blah, 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 while following the rules. Okay, maybe that can be omitted, right? And at some level, this is just restating the problem, but in the handwriting of a child, right? So this is when I do it ahead of time. So assuming the n smallest rings are on A, let's move the top n rings from A to B. It's precise. Not much thought actually really has to be put into it because this is more or less the problem I initially gave. Okay. But this is a contract. So I want to implement this exactly, but I can also rely on this contract for any subproblem. Okay, so by the time you've got this down, you've basically identified all the subproblems and you've largely deconstructed. It's going to be tough to screw it up now that you have the right sentence. But let's see if we can. All right, so let's implement this. So I put the sentence on top, just a recursive spec, and let's just write some pseudocode. It doesn't have to be too formal. You can say, oh, move this, move that. But I want to force you guys to participate. So what would line 1 be? Yeah. Okay. If n is 0, what should I do? Great. Return. Okay. Sure. Okay. Oh, well, I guess we're just committed to this sentence. So assuming the n smallest rings are on A moves the top n rings from post A to post B. Does that answer your, yeah. Yeah, this is actually a little more specific. That's right. So the initial session of three probably wasn't detailed enough for us to, yeah. I guess so. At some level, I'm not too concerned, right? One thing actually kind of nice that's going on is that when I only focus on the top five rings, I can completely ignore the bottom two rings, right? Because they won't get in the way. So somehow it's a distinction that we don't have to worry about as long as we're precise. Okay. All right. So that's this base case, n equals zero, return. Nothing surprising. So I'll just write explicitly. Otherwise, n is greater than one. Okay. So now, what can we do? Yeah. Okay. Move top. Oh, so actually, let me do this. I'm going to ask you to use our function. So what parameter should I put in if it's TOH, Towers of Hanoi? N minus 1, A, B, C. I think someone else said C. So now we have to be a little bit careful about the sentence. So whatever B is the post we're moving to. And then whatever C is sort of our leftover post. And in this case, I think what we want to do is we want to move the top N minus 1 out of the way so we can move the bottom to B. Okay, so we'll write C instead of B and we'll swap them. Okay, so this is the power of writing A, B, C instead of just three posts. If it was just three posts, we wouldn't be able to make this distinction very clearly. But with A, B, C, now you have a lot more power. This is often the case if you make your like recursive spec more detailed, more useful, or more detailed, then it becomes more useful in those subcalls. Okay, so you've done that. You've moved n minus 1 from A to C. Now what? Yeah, move 1 from A to C, to B, sorry. Okay, good. Move 1 from A to B. And then, all right, so the parameters would be n minus 1 and then what? Okay, good. N minus 1 C B A. Okay, you move all n minus 1 back, right? Okay, so it's very simple, right? At some level, like before, we were like moving all these rings, and it felt like I don't know how long this will take. The cognitive load of this algorithm is very low if you're okay with recursion. And usually, the better the sentence, the stronger the sentence, the more firm you feel about it, the easier that magical step becomes. So, okay. So if we're going to prove correctness, and I'm going to be a little bit quick, since it's a lecture, you don't want to see me write out paragraphs, right? So if we want to prove correctness and kind of following sort of that approach from the staircase example, right? The first step, as you guys know, like by heart, I'm sure somebody tortured you before. Okay, you worry about some base case, right? So base case n equals 0. Oh, there's nothing to do. Of course, the algorithm's correct. You might write a sentence to that effect. I won't write it here. So the more interesting case is, okay, will it work for any arbitrary number of rings greater than 0? Okay. And you would say something like, okay, the key thing is that you know, sort of the wording would be like by induction on n. Okay, so this is your recursive spec becomes your inductive hypothesis. And then by induction on n, TOH n minus 1, ACB moves, I mean, it's almost like rote copy, right? Moves the top n minus 1 from A to C and something like this. And you just say, oh, by induction, it does these two steps are correct. And I move one over and there's no violation because everything's on C. And then by induction, that last step will correctly move everything back. Okay. You should mention, I didn't write it out, but the first sentence would have been, we will prove by induction that TOH and ABC will, assuming the n smallest rings are on A, moves the top n rings from post A to post B. Okay, so just establish what the inductive hypothesis is, and if you get the recursive spec right, it's just the same thing. So there's not a big gap between the recursive spec and the inductive hypothesis. Inductive hypothesis is what you might have been exposed to in discrete math or something. And I think the only point of emphasis here is that, at least when I took discrete math, I was like doing all these like little puzzles and stuff or getting some equation. But here we're going to make it algorithmic, right? So we're going to try to make this a tool. It's really the idea of breaking down a big problem into slightly smaller problems as one way of managing complexity, right? So this is a bit of a toy problem, but the general motion is invaluable. Okay, that's a rushed, sketchy proof. Okay, so then you'll conclude that it works for n, and that's all you need to show. But just a generic n. You don't have to obviously enumerate the n's. Okay. Let me give a slightly harder version of the same puzzle. So before I was just worried about like how do you move the rings at all. Now I'm going to be a little more strict and say I want you to truly use the minimum number of moves and be able to justify that it's truly the best possible. Clearly it's like a big combinatorial thing, right? So it's not obvious, right? We have some solution to move the n rings over. Now I really want to get the best possible solution if I'm only counting the rings. I'll give you guys a chance to look at it or check Instagram or whatever. All right, anyone have any ideas for trying to really minimize, in a strong sense, the number of ring moves? Even suggestions to get the discussion going. Yeah. So intuitively, it felt like our algorithm didn't have much slack. Did have to move the top n minus 1 rings out of the way before you can move the bottom one over, right? So, okay. Then suppose I told you this was even the right algorithm. But now how can I take that intuitive argument and really make it formal? How can I then prove that this algorithm is truly optimal? Yeah, I agree, but I want to expand the part where you said basically we have to, and I want to figure out how do we get that down on paper in a precise way, right? So I think we're all kind of on the same page. It seems very intuitive. It's certainly true. I just want us now. We're practicing the part where we formalize it and get it on paper. Yeah, yeah, we can use induction. So all you have to do is just strengthen your sentence. Okay? I'm no longer implementing this thing to move the n rings over. It's going to move it with the minimum number of moves. Okay? And I'm going to say, okay, this is now what I'm going to implement, right? I have a stronger contract. And then that'll let us sharpen up and I think cover over the basically part. Because now, okay, you have to argue that in order to, you know that you have to move the bottom ring from A to B. Okay? And to do that, you have to move the n minus 1 if, by any method from A to C just to get it out of the way, right? And you know you'll have to move it back afterwards. So those are the things you have to do. But the key point is that by induction, this is the minimum way to get them out of the way. And this is the minimum way to put them back. Okay, so I don't know. It seems like a trick, but it's quite sound. Okay, and it's very nice because we didn't have to do the algorithm didn't get more complicated. We just had to sharpen our understanding, and it's just encoded in the spec. Okay, the key point is please write this sentence on your homework. Okay. Any questions? Okay, good. We're making good time as well. I was worried that. Okay. All right, on to another problem. Maybe you've also seen this. Okay, given two numbers x and y, I want to compute the largest integer that divides both of them. That's called the greatest common divisor. Okay. I'm pretty sure in past classes I covered up the 580 and asked students to try to solve this, but I forgot, so spoiled the fun. Okay. But I guess if you plug that into Google, you'll find that the greatest common divisor of those two numbers is CS580. Okay, especially if you haven't seen it before. So my goal is to make an algorithm to compute the greatest common divisor. Does anyone want to suggest any fun ideas? I feel like it's always good to give you all a chance before I just show you the answer, because that's sort of not nice. So I give you two numbers. You want to get the greatest common divisor. Yeah. Yeah, so good. So we're going to basically build on that observation, which I guess is due to Euclid. But okay, let's say that x is the bigger of the two numbers. Okay. Some level I want to get the numbers smaller. Like hard numbers are hard. Smaller numbers should be easier. So I know that, whatever the solution is, if it divides x and y, then it's going to divide y and x minus y. Okay, so maybe I can just take this and subtract y and just keep getting down the number so small, right, that we kind of terminate. Okay, so we'll do a recursive algorithm then. I guess you can do a loop, but I'll force us to do a recursive algorithm. Okay. So I wrote GCD XY to get us started, and now you need to write the sentence. Okay. Sure. If x greater than y, or assuming x is greater than, you can do either, but okay. You're writing the sentence, not the code. So I want to just say, what's the input, what's the output? We'll do the code next. Sure. Assuming x is at least y, returns the, I guess GCD, okay, of x and y. It almost feels like we're not saying anything, and that's sometimes appropriate. Okay, but at least we've made it clear. And assuming we all agree on the definition of greatest common divisor. All right. Okay. So that is, I guess, our recursive spec. Okay. Oh, I guess I also specified uh, probably x greater than 0 and y greater than equal to 0. If the numbers start getting negative, then it's going to be kind of messy. Okay. Oh, okay. So let's implement it recursively. Okay. And here we'll just assert that x is greater than equal to y. So your code will crash if it doesn't. Okay? And we'll let the user know. Make sure x is greater than equal to y. Okay. Okay. So what would be what would I write? What would be the first line of the code? Sure. What would be a base case? I guess they're both non-negative. So maybe if y equals 0 suffices, then that's right. So I guess as GCD is defined, everything divides 0. So if the small number is 0, then x is the best you can do. Okay? Clearly the GCD is smaller than x, so x is optimal. Okay. All right. Otherwise, y is not 0. So return GCD of x minus y, y. Does that look good? No. The what? We should check the assert. So maybe I'll write like, maybe I should have done an if statement or something, but A, B, where A is the maximum of the two, and B is the minimum. Okay? So just have to be careful. The way we set it up, we didn't have to do it this way, but we set it up so that x is always greater than equal to y, so we just need to make sure we fulfill that contract. Okay. Great. I think that's what we have. Yeah, yeah, that's true. That's true. But that would also start up here. I've already, yeah, then we'd also go up and change the sentence. But we absolutely could have done that. That's often the case. But here for whatever reason, I've typed this one up, so we're stuck with it. Yeah. But absolutely, you could have left out x greater than equal to y and then added some swap statement or if statement at the beginning. Okay. Um, how would you prove correctness? I think this would be, again, once the sentence is set up, there's often very little left to do. Uh, it would just be like, okay, the base case. Oh, actually, no, there's some more thought to be put into this. Okay, I want to prove correctness, and we want to prove by induction since that's the name of the lecture. So you need to figure out what you're going to do induction on. Like, okay, now I'll take this. In other words, we'll do something like this. You might write something like, we claim that GCD XY fulfills, because I don't want to write out the whole specification, the specification, which is written above, maybe we can write, we prove that GCD XY is equal to this sentence. But you need to identify the stairs of your staircase, right? By induction on, by the GCD of x and y minus x. Sorry. Okay, so just to make sure, something like this. Well, okay, so you're trying to identify some quantity that gets smaller, but actually our argument was based on the fact that this GCD is the same as the input, so it's not even actually getting smaller, right? So we want to identify something that's getting smaller so that it reaches some kind of bottom. Yeah. Oh, we can do induction by x plus y. This will always get smaller. Okay? All right. So this is also going to be a little bit awkward. Okay. What would be a base case? Yeah. X plus y equals 1. Maybe a base case. Okay. And then, okay, if x plus y is equal to 1, then I guess x has to be equal to 1. Y has to be equal to 0. And this returns 1. Which we think is okay. Obviously, I'm being a little bit loose here. Okay. That's one base case. I think we feel good about this. Okay. Um, okay. So what next? Yeah, sure. All right. What happens if x plus y is greater than 1? Now, maybe I'll note something that's a little bit odd, is that even within x plus y greater than or equal to 1, it's somehow like a little bit different than our if statement, which is guarding against y equals 0. Could we do the induction on y? Let me make us some. Yeah, okay. Suppose we did induction on y then. Okay. If you wanted to do induction on y, uh, if y is equal to 0, then we're okay. If y is bigger than 0, sorry, y is bigger than 0, then, okay, you're going to do a recursive call to x minus y, y or something, right? Now, okay, what's one challenge about this? Y might not actually go down from one to the next. So actually, I think x plus y is okay. There's going to be ultimately a couple different ways you could have done it, but we'll stick with x plus y. Oh, well, okay, so let's say that x was 10 and y was like 2. The next call will be to 8 comma 2. But y didn't go down because y is still 2. So if we had just set up by induction on y, you couldn't say, oh, by induction, I can handle this subcase, because y was the same. Yeah. Okay. So we could still use x plus y as progress. That's actually not that big a deal. And you can just say, oh, okay, if y is equal to 0, then, whatever, this step is okay. Everything is okay, right? Now, if y is greater than 1, maybe this step part is more interesting. We would write Somehow I just want to get that sentence where we do induction on x plus y. Yeah, do you have an idea? Yeah, so what I want us to do is I want us to very precisely, sorry, I want us to very precisely ultimately invoke this sentence on something smaller, right? And say, oh, that sentence I know it's going to work because it's smaller in the quantity that I'm counting. Yeah. Okay, let's do it a little more top down with sort of more of a recursive feel. So maybe we should clarify something. So last time I think we said, oh, by induction I assume it works for n minus 1 rings or something, right? But here we can say, sorry, I'm not using my space super well. We can, all right, let me draw this line. We can assume by induction that GCD xy is correct for all x plus y less than n. Okay, a slight distinction in saying just equal to n minus 1, because of course, now it may be arbitrarily small, right? And this the assuming taking this mathematical fact for granted, all I need to do is argue that this subcall is correct. I feel good about the use of the subcall. It should be the GCD of x minus y and y. But what's just this last part where we invoke induction? How would I actually write out that whole sentence to just say this is correct? I do need to justify that this sum went down. Okay. So again, I'm a little hurting for space, so this is not as fleshed out as it should be. But you would point out that, okay, if I add them up, no matter what the max is, right, we're in the case where y is greater than 1. So the sum will be x minus y plus y, which is x. And how does that compare to x plus y? Because we're in that case where y is at least 1. Okay, so it's a detail, but it's important to actually connect the argument together. You really point out, something that I'm doing induction on really went down. It really is a lower stair on the staircase. So you do need to make this distinction. These might seem like simple examples, of course, but it's good to get the basics down before things get more complicated. Okay, so that's it. Obviously, if you type it up, it'll look smarter. Okay, what's the running time of this algorithm? If you agree it's correct, what's the running time? In the worst case, I give you two numbers, x and y. O of largest number. Okay? And what would a bad case look like? Sorry? Yeah, this could be like a gazillion, and this could be like 1 or something. You're just like subtracting 1 every time? Yeah. Okay. So, okay. I kind of blew it, but oh well. Let me ask another question. Is this a good running time? Is it a linear running time? Right? X is the input. It's O of X. Is that linear time? Okay. Who says yes? Oh, this is my favorite, actually. Do we have time? Okay, it's okay. Who says yes? Okay. And then who says no? Okay, so 60% already out of it. Week 1. Okay, great. All right. So most people said yes. No one said no. But if I give you X as an integer, How much space is it taking on your computer? Sorry? Okay, well, suppose it could be arbitrarily big, but as a function of x. Log base 2 of x, I heard somewhere in the crowd. Okay? So actually, x or x plus y, doesn't matter because y is smaller than x, is actually exponential in the input size. Okay, and usually we think exponential running times are bad. Okay, so we're going to try to do a little bit better, right? So sometimes with numbers, you need to watch out for this. What is really a polynomial running time? Oh, what's my actual input size? I'm really interested in what's the running time as a function of the input size. All right, so as you pointed out, the bad case is like a really big number and a really small number, right? This will go to like 98, this will still be 2, this will go to 96, this will still be 2, right? This will be 2 all the way down to like the very bottom, right? Until finally we get like 0 and 2, right? So that's absurd. So what would you do in this case that would be much smarter? Yeah, we can do modulo, right? So instead of doing x minus y, suppose I looked at x mod y, right? Same thing, right? So x is equal to ky plus r for some k. And so that tells you that if q will divide x and y, if and only if q will divide y and r. Okay, and hopefully r is going to be smaller. Okay, r will certainly be smaller than y. So you can do an algorithm like this, where given x and y, you do y and x mod y. Okay, here I think y is always bigger because it's modulo y, which I think is why I set the sentence in that particular way earlier on. Okay, and you can do as usual, just like before, some kind of proof by induction. We feel pretty good about y equals 0. In the case where y is greater than 0, we just need to point out, oh, okay, we'll do something different, slightly different. In that this time we can actually do induction on y because y always goes down, right? The remainder is always something smaller than y. So in fact, maybe this proof is even shorter because you can clearly see y goes down, and I say, okay, it works for the next call because y went down. Okay, being a little quick because we're running out of time. I do want us to try to figure out the running time of this thing. It feels like this is more aggressive. It shouldn't be any slower. But how can I argue it's much faster? How can I try to analyze the running time of this algorithm? Yeah. Yeah, and how to argue about it too. Okay, so let's say it's going to be like log x or something, where x is the bigger number. How can I argue that it's log x? That means something should be really being cut down rapidly, right? How can I argue it's log x? Okay, it's not obvious to me that's the worst case, but at the very least, there's other ways to maybe argue. It's not obvious. Yeah, you might still be right, but I have a little trouble seeing it clearly. All right, let's break it up into two cases, right? Okay, what happens if y is at least x over 2? Yeah. Uh, yeah, so when I take x mod y, well, okay. Let me rephrase a little differently. What if y is at most x over 2 first? Let's do that first. Okay, so then that remainder is going to be at most half of x over 2. So you're making a lot of progress now. Okay. And now, what happens if y is at least x over 2? It's a good question, actually. Sorry? Uh, oh, right. And the remainder is still, again, at most x over 2. Okay, so out of the sum of the two numbers, you're chopping off like half at a time, and then you push that through and you'll get log x. But that's where your 1/2 is coming in. I won't flesh it out, partly because we're out of time. Okay, but it'll be in the notes. Okay, that's it for induction, and I'll just keep answering questions here. But otherwise, we're out of time. Thank you.